Hi, and welcome back to our flipped chemistry classroom. Today we're continuing with our lessons about gas laws, and we're wrapping up with the ideal gas law. So far we've talked about the proportionality of volume to moles, proportionality of volume and pressure, inverse proportions, and relationships between volume, pressure, temperature, and moles. So we have at this point 6 different gas laws that we've learned: Boyle's law, Charles' law, Gay-Lussac's law, Dalton's law, the combined gas law, and Avogadro's law. And now we're going to put all of this together into one law that we call the ideal gas law. Unlike the other laws that we've talked about so far, this one isn't about changes. This one is a calculation at any temperature and pressure. So our ideal gas law, remember, just like our kinetic molecular theory, describes an ideal gas. So it is really close to being accurate at pressures around 1 atmosphere or less, but we're going to treat it as if it always works. And we'll talk about what the exceptions to the kinetic molecular theory and the ideal gas law are. So here's our ideal gas law. PV equals nRT, where P is our pressure. And this time we want to make sure that our pressure is in atmospheres. V is our volume. And again, we have to be specific. This is the volume in liters. N is the number of moles. And now R is a constant. This is called the proportionality constant, and its value is 0.08206 liters times atmospheres divided by moles times kelvins. So this is why our pressure has to be in atmospheres and our volume has to be in liters, because if that's not the case, then it's a different R value. And we do have several different R values. This is simply the one that we'll use. And so we want to always have pressure in atmosphere and volume in liters. And of course, as with all of our other calculations with gas laws, our temperature is going to be in Kelvin. So here's our example problem. At what temperature would 2.10 moles of N2 gas have a pressure of 1.25 atmospheres in a 25-liter tank? So we're going to just quickly work this out on the board behind us. So we have N equals 2.10 moles. And we have pressure is equal to 1.25 atmospheres. And we have volume is equal to 25.0 liters. And we know that R is equal to 0.08206 liters times atmospheres over moles times Kelvin. And we're being asked to find the temperature. So T is the thing we're solving for here. So now we're just going to plug all of this into our equation. PV equals nRT. And so our pressure is 1.25 atmospheres. Our volume is 25.0 liters. Number of moles is 2.10 moles. R is 0.08206. And then temperature. And we're going to solve for temperature. And so we have 1.25 times 25 divided by 2.1 divided by 0.08206. And we get a temperature of 181 Kelvin. So our temperature is equal to 181 Kelvin, which is pretty cold. So pretty simple and straightforward to solve these sorts of practice problems. We just write down all the values that we have, plug them in, and solve. Okay. So that's the ideal gas law, and we'll talk in class about the exceptions to ideal gas behavior. But let's go ahead and jump into gas stoichiometry. So the beauty of gas stoichiometry is that it's super, super simple. Okay, so we remember Avogadro's law that says equal volumes of gases at the same temperature and pressure contain the same number of molecules, or volume is directly proportional to the number of moles. So this means that molar ratios can be expressed as volume ratios. If we have 2 moles of hydrogen reacting with 1 mole of oxygen to form 2 moles of water, that means that 2 liters of hydrogen are going to react with 1 liter of oxygen to form 2 liters of water, because volume is directly proportional to the number of moles. So that means that in gas stoichiometry problems, we can skip converting to moles. We can simply convert from, we can use molar ratios as volume ratios. So in this practice problem, our oxygen, we have 1 mole of methane reacting with 2 moles of oxygen to give 2 moles of carbon dioxide and 2 moles of water. So if we want to know what volume of oxygen gas would be needed for the complete combustion of 1.50 liters of methane, super simple problem. We have 1.50 liters of methane. And we know that for every 1 liter of methane, we need 2 liters of oxygen. And so we need 3.00 liters of oxygen. So we don't have to convert from liters to moles and moles to moles and moles to liters, because at the same pressure and temperature, the volumes are directly proportional to the moles. And so we can use molar ratios as volume ratios. All right, so that's it for gas stoichiometry and the ideal gas law. As always, I look forward to hearing your questions in class. See you soon.